Hi all, this is Lakshmi, working as assistant professor in the Department of ECE at SNSCT. So today I'm here to discuss about the title BJT and FET biasing. So under which we are going to discuss about the biasing type, which is DC bias with voltage feedback. So we call this type of feedback biasing as collector to base bias technique. So in the previous session, we have learned about fixed bias, and we found that it is the stability wise, it is not much good compared with the other types. So we are preferring this type of voltage feedback bias for better stability. So you can see this is the circuit of DC bias with voltage feedback. So in order to improve the stability, we have included a feedback resistance RB in the circuit. So here we could see that from collector to base there is a feedback. So this RB is acting as a feedback path from the collector to base. So here in such type of operation, the operating point, it slightly depends on the transistor parameter, which is beta, which is called current amplification factor. So when there is a feedback included here, what actually happens inside the circuit is, if there is any increase in the output current, that is collector current, due to any temperature variations or other parameters, if there is any rise in collector current, so there would be a rise in our VCE also. So, which would again, since there is a feedback here, so there would be a rise in the base current. So, what happens is, so this the value of RB will increase. So, increase in this resistance, base resistance, would compensate any change in the further increase of this collector current. So, thus the circuit or the system is maintained stable. So the compensation of further increase in the collector current is done with the help of this feedback resistor. Hence this circuit is called collector to base bias, because from collector to base we have a biasing feedback resistor. So the other name for this DC bias with voltage feedback is collector to base bias circuit. So here also we are going to do the analysis by considering the input circuit first. So input circuit here means, so we consider the base and the emitter loop. So base emitter loop, when this is considered, so the same analysis we do here, we are going to apply the KVL, that is Kirchhoff's voltage law, which means the algebraic sum of voltages around the closed loop is equal to 0. So on applying that, so we would get PCC minus IC RC, that is I dash C RC, and minus IB RP, that is the voltage drop here, minus VBE and minus IERE equals 0. So on solving for the value of IB, we would get the equation as IB is VCC minus VBE by RB plus beta into RC plus RE. So we could find that there is a stability obtained here. And analyzing our output part, that is our collector emitter loop. So previously we have considered the input part, base emitter loop, and now we are considering the collector emitter loop. So when I consider this and do the analysis, apply KVL, that is Kirchhoff's voltage law, algebraic sum of voltages around the closed loop is equal to 0, we would get this equation, that is IERE plus VCE plus IC I dash C RC minus VCC is equal to 0. So solving for VCE, we would get the equation for VCE as VCC minus IC into RC plus RE. So this is how we analyze and find the operating points. So as discussed, so we have discussed that the stability of the system is identified with the help of a stability factor. So generally, stability factor means the change in the value of the collector current, that is IC, with respect to three parameters of the transistor. One is beta, the other one is VBE, and the other one is ICE. So beta is our current amplification factor, base emitter voltage, and the reverse saturation current. So the variation of the collector current with respect to these parameters, we call it as stability factors. So generally the beta will increase in temperature, whereas the VBE that would decrease with respect to 2.5 millivolt per degree Celsius, and the reverse saturation current will double for every 10-degree increase. So these are the parameters to be considered while analyzing the stability of a system. So, as I told, for the better stability, the circuit should have the stability factors, which is given as S, S dash, and S double dash. So, S here will be the variation of our collector current with respect to beta. So, that is S of beta. S dash will be with respect to change in the collector current with respect to base emitter voltage, and whereas S double dash is del IC by IC naught, that is change in collector current with respect to the reverse saturation current. So these are the stability factors which we have to take into consideration to determine the stability of the system, with especially varying with the temperature. So today's assessment is discuss the advantages of collector to base bias circuit. So here the circuit is very simple, as it needs only one resistor and it provides better stabilization for less changes. So we prefer collector to base bias circuit than our fixed bias circuit. Thank you.